Yeah, I'm gonna beat you up for a video. So.
Oh my gosh, and Jimmy Miss Coleman is subbing in gym class.
What is she making idiots?
We're touching tips. Why are you laughing? We're touching the tips. Really? Why are you laughing? Do you not like touch tips with everybody? You're confusing me. Chill out, we were just touching tips. Like, what's wrong with that?
And there's another one.
What?
Sorry, she got a big old face.
Really?
I don't write it. It was like people who genuinely like fight. Fist fight. Bingle with someone else. Yeah. I think were they blue? No, that's brown. Yeah. That was 6th grade year one.
I gotta drink some water.
Oh, who did that?
It wasn't the site, but it was.
Crazy.
That's not crazy.
You want to see me draw a cutesy little eye? Oh my god. I messed it up. Okay, it's so cute.
Let's we have them all. Everyone has a copy on their papers, or has a copy of them where they can at least see how they're done.
Okay,
And then we'll
this
move
is
on
the
to
eye,
next step.
guys.
So the first one says to create an expression that has 3 terms. Does this have 3 terms? Yes. Check mark. Check. The first should have a coefficient of 7. Does the first term have a coefficient of 7? Right, it does. So that one's good. The second should have 2 factors. Is there 2 factors?
Yes.
Yes. Does one of those factors have 2 terms in it? Yes. So these 2 are multiplied, 2 factors, but this one has an added side of it. Perfect. And the third one should be a constant term. Is that a constant term? This one is completely correct. Now, is it the only one? No. There's literally infinite correct answers. Could I put 7z here? Yeah. What about 7x squared? What about 7x to the 5th? Yes, doesn't matter, as long as the coefficient is 7. Can I put minus 372.7? Yes, as long as it's constant. Is everyone good with that one? See like how the terms and factors work here. So this one. You have 3 red shirts, 2 blue shirts. 4 pairs of red shorts, 3 pairs of blue shorts. The light bulb has burned out and you can't see what you're picking. Now, when you're doing that, can you still tell the difference between a shirt and pants? Yeah. Yes. Right. So you don't have to worry about that. You just can't see what color they are. So when you pick the first one, let's say we're doing shirts first. You have an option of it could be red or blue. There is a 3 out of 5 chance that the first one's going to be red because there are 3 red shirts and 5 total shirts. 2 blue shirts, 5 total shirts. Alright? Now, if you pick a red shirt out, the only option you care about after that is that the shorts you pick are red. Are there other options on that path? Yes. Do I care about them? No. I only care about the ones that I want. There are 4 out of 7 pairs are red. 3 out of 7 pairs are blue, and I'm only going to follow the blue path because I only want matching. So I only want blue, blue, and red, red. That's it. I don't want anything else. If I'm going to follow one path to the end, I multiply all the probabilities. So 3/5 times 4/7 goes there. 2/5 times 3/7 goes here. So this represents the chance that I get two red things in a row. This is the probability that I get two blue things in a row. If I want more than one path, I add the results. So there's an 18 out of 35 chance that I get a matching color when I pull two things out of hand. Okay, that's perfectly correct. Does that make sense? Other questions about either of those two before we move on? Thank you guys for putting those up. Okay, so we're going to start today looking at a specific type of expression that we use a lot, which are exponential expressions. We're going to have to use these properties quite a bit when we do things, especially later when we start simplifying expressions and defining expressions, and multiplying them, and all that kind of stuff. Every one of you has seen this already. We're just going to give formal definitions to things. An exponent is a mathematical way to show repeated multiply. If I'm going to multiply over and over and over again, that's an exponent. Which is why if I'm going to do 2 to the third, it's just repeating multiply by 2 3 times. Not new. Everyone's seen this years ago. Right? So that's not new. In general, if I have something to a power, the general definition is that's just a times a times a times a times a n times. This little tiny one up here is what we could call the exponent. Right, that's a common misconception. The whole thing is not called an exponent, just the thing on top is called an exponent. And a lot of times, we don't actually name this thing, but we're going to have to refer to it. That's called the base. So in 2 to the third, 3 is the exponent, 2 is the base. Are we good with the terminology? Right, again, the concept is nothing new. Okay, what we're going to do with it might be, but this is not.
You wait a minute.
I'm just putting it on top. So, what we want to do is we're going to develop a couple of rules. The first one's going to be, what do I do if I multiply exponential terms that have the same base? Right? And that's why I introduced the word base if you weren't familiar with it. The base has to match. So I'm going to take a look at this and figure out the pattern. You may already know it, but we're just going to show that it's going to make sense and we have, and that's how it's going to work. If I have x squared times x to the third, x squared means what?
X times
X times x. So that first thing is just this. And I'm multiplying that by x to the third, which means x times x times x. Right? 3 of them. When I write it this way, as opposed to x squared times x to the third, does it really seem necessary to separate them? How many do I really have?
5.
Right? I really have x times itself 5 times. Right? And we can kind of see how that pattern's going to work. If I have something to a power, and I multiply a term that has the same base with another power, regardless of what that is, I don't care, regardless of what that is, I can condense that down into that same base, but I add the powers. Right? This is the multiplication rule for exponents. If I multiply 2 things of the same base, I add the exponents together. And it doesn't really matter what those are. Like if I give you a problem like this, and I say simplify that. What if I have b to the 91st times b to the 31st? Right, those are really high powers, but who cares? Whatever it is, I know it's b to the 122nd. Regardless. I don't even need to understand what B is, I don't need to know what raising something I don't know to the 91st even means. I know that, hey, if I raise it to the 122nd, it's the same thing as the multipliers. Does that make sense?
Yeah.
Back to the top, so I can move on. The only other rule we're gonna look at today, there's only 4 rules we're gonna look at total, we'll look at the other 2 tomorrow. But the other rule is gonna be, well, what happens if I take something that's exponential and I raise it to another power? So I have x squared to the 3rd. Again, what does to the 3rd mean? Multiply it by itself 3 times. So the thing that I'm multiplying by itself is x squared. So is anyone in disagreement that those 2 are the same thing?
Yeah. No.
So everyone agrees. X squared to the 3rd is x squared times x squared times x squared. And we've already established what do we do with exponents when we multiply?
Yeah.
Add them. So exponents are what we do for repeated multiply. What do we call repeated addition? If I add over and over again, what do we call that?
Multiplication.
We call that multiplication. Right? That's all multiply is, right? 2 times 3 is 2 plus 2 plus 2. 5 times 4 is 5 plus 5 plus 5 plus 5. Right? It's just 5 4 times. One. Sure. Okay. Tiffany Applegate. They want you in the office. They said bring your stuff. Okay. So if repeated addition is just multiply. Oh, look at that. 3 times 2 is 6. So it shouldn't be that surprising that if I say, hey, the rule in general is if I have an exponent term raised to another exponent, I can simplify that by multiplying. Here is the way that my brain, and it may not make sense to yours, but it does to some people, of how to differentiate what we do and when. How many of you remember the order of operations? PEMDAS.
You just said that.
Well, why don't, when people say order of operation, I don't know what you're saying, but when you specify PIMDALs, then I
Well, it's the same thing as y equals mx plus b.
Yeah.
That's actually called slope-intercept form. It's a formal name versus the abbreviation or like the simplification. Order of operations is its official name. It's just like you have a full name and a nickname. Right?
Yeah.
That's all it is. It's just that's its acronym. As long as you don't even have to remember it's called order of operations. Just remember PEMDAS. Whatever it is that you're doing here. So if I have power to power, that's an exponent. It always goes down one thing. Right? So if I do an exponent, I multiply it. I multiply it. If I'm multiplying, I'm going to go to the next thing that makes things bigger, which is add. So exponents go down 1 to multiply. Multiplying goes down 1 to add. It always goes down 1. It can't skip over. It has to go down one thing. Does that kind of make sense? So I'm going to know right here, I'm not going to multiply because I already have multiply. I have to drop it down 1. I have exponents, I have to drop it down 1 to multiply. Right, and I'm not going to add them because exponents are too high above add. Or, yeah, does that make sense? So I'm going to walk through this example, and then I'll give you the time to work on the rest of the practice problems that I have. This says simplify the expression, and that's going to be the